All right, ladies and gentlemen, thank you for playing this. We're going to talk about heat transfer and what we mean by that. So I'm going to stick with red. So heat transfer. So we're going to talk about how energy moves. So I'm going to have two objects. One's hot, one's cold. And if we have to look at the third law of thermodynamics, the temperature between those two objects that are touching each other will be equivalent between the two. And we're going to look at how this happens. Now, when we talk about two objects, we commonly think of two solid objects touching together. But this can be a hot object in the air, to a water in the air. So, it doesn't matter what phase the object's in, but two objects touching each other. If nothing else is going on, the temperature will equilibrate between the two. So when we look at this, and we talk about a non-reactive energy of the object, and basically the atoms are moving. And either the molecules moving or the atoms are moving. And what we got translational, which means they're traveling from one place to the other. So atoms going like this. It's translational. They're moving. They have kinetic energy. Vibrational is basically vibrating on a spring. So we've got two atoms connected to each other, and they're going to get closer together, and then they're going to go farther apart. They're vibrating. They're going back and forth. Or they may pivot, and they may go back and forth like this, in and out. And rotational is they spinning. The atoms are spinning, or the molecules spinning. So we have, say, this is water. This is moving this way, and this is moving like this, and this may move down. So it's rotating. And this is what the three types of motion that atoms and molecules have. And all of them have particular types of energy, particular amounts of energy. Now, when we look at energy, energy has to go from hot to cold. Because if things collide or they touch, things are going faster, we'll transfer the energy, something goes slower, and they're going to end up averaging out. And this is where we say energy flows downhill. Flows from high to low. Always. To get something up to a higher temperature, you got to add energy to it. So three types of motion or movement of heat. So let's take a look at this. So we got three ways that heat or energy can be transferred. And we have conduction. And collisions between atoms will cause an energy transfer. So we're talking about two things touching each other. The atoms are touching each other will end up transferring energy between each other. And most of the time it's going to be high to low. Rarely do you go low to high. But theoretically it can happen, but it usually doesn't. And this usually occurs mainly with solids and liquids. You put hot solid into water, it's going to cool down fastly and transfer the energy from the hot solid to the liquid water. Convection is the movement of fluids, liquid and gases, that transfer heat. Our heating systems are based on convection. You go home, you turn your heater on. If you have an old-fashioned radiator, all those are moving liquids through something to generate heat and transmit heat throughout the house. And convection is very effective in moving energy across a distance. So when we talk about, say, air conditioning a house, you're blowing cold air into a big room. And that cold air comes from the compressor or the chiller somewhere outside your house. So it's taking fluid, air or gas or liquid, through to where we need to cool or heat. The last one is radiation. And when we talk about heat, movement of heat, we always think about infrared radiation. That is the wavelengths in the wavelengths longer than infrared, or longer than red. It usually occurs, but any type of radiation is transfer of energy. So here are the three types of movement of heat, movement of energy that we're going to look at. So we're going to go back to our example and take a look at how these things can affect, how the objects can affect what the final temperature is. And so this is going to be important. Heat loss equals heat gain. So object 1 is going to lose heat, object 2 is going to gain heat. And whatever energy is lost from object 1, object 2 is going to gain it. I'll always go from hot to cold. And that's important. So let's take a look at what's happening. So scenario 1, both objects, same material, same size. Find the average temperature between the objects. This is going to be the final temperature. So temperature 1 plus temperature 2, divide by 2, that'll give me temperature final. That basically is the average between the two. This only works if this is true. If object 1 and object 2 are the same material and the same size, if they're different materials, this won't work. That goes to scenario 3. But let's look at scenario 2. So we need a little bit more information. So we've got both objects, the same material, but different size. And what we need is what we call heat capacity. So we need this constant physical property. It's basically heat capacity is the ability of that, how much energy it will take to raise the temperature of that object by 1 degree Celsius. Excuse me. So energy, amount of energy per gram per degree Celsius. That's what we call the heat capacity of an object. We usually determine a specific heat. We have so much mass of an object, to move it 1 degree temperature for 1 gram. It takes so much energy. So we have 50 grams. Move it 1 temperature, and then it takes 50 times more heat, so on and so forth. And so we're going to use this equation that that energy is going to equal mass times the heat capacity, Cp, times the change in temperature. We call this delta T, where delta T is Tf minus T initial. And we're going to use this equation. So this is energy or heat that is given off or absorbed is equal to this. Now for this, we're going to specify that our object is going to be 100 grams of water at 60 degrees Celsius. Then we've got another object of water, 10 grams of 20 degrees Celsius. And our heat capacity is this one. Remember this will always be true. Each element, each compound, each material will have its own heat capacity. Sometimes they're very similar, but sometimes they can be different between each other, and it depends on the phase as well. So the heat capacity of water, of liquid water, is going to be this. So heat flow is mass times the change in temperature times the heat capacity. Guys, you can switch this back and forth. You're going to have mass over here or Cp. It doesn't matter where you put it because they're all multiplied except for what's in the parentheses. So heat loss equals heat gained. So here's our. So what I'm going to do is move this over to this and rewrite this. I'm going to rewrite it as M1 times Cp times Tf minus Ti is equal to negative M2 Cp Tf minus Ti. Now this is going to be 100 grams of water, and this is going to be at 10 grams. So we're going to look at the left side first and the right side. But one thing we're going to do is remember Cp is the same number. So this actually cancels. So I have M1 temperature final of 1 minus initial temperature of 1. That's equal to minus M2 times T final of 2 minus Ti of 2. Now, folks, since M1 and M2 are going to be touching each other, these things are going to be the same temperature. By definition, the final temperature of object 1 and object 2 have to be the same thing. So M1 times the final temperature minus M1 initial temperature is equal to minus M2 final temperature minus M2 initial temperature 2. Well, initial temperature on one side, remember, is 60 degrees, the other side is 20. So M1 temperature final, and I'm going to put the, let's see, rewrite this as 100 grams times TF minus 100 grams, this is going to be 60, is equal to minus 10 times TF minus 10 times 20. And we're looking for TF, so we've got to move the TF over to the left-hand side and by adding both sides by 10 TF. So that'd be, and that has to be a plus, excuse me. So 110 TF is equal to 6,200, because 100 times 60 is going to be 6,000. 20 times 10 is 200. So I'm going to end up with 6,200. So on the right-hand side is 6,200. So our final temperature is going to be 6,200 divided by 110. It's going to be 56 degrees. 56.4 degrees Celsius. Sorry about that. And that's the final temperature. So what happens is that since there's a lot of water at 60 degrees, it's going to decrease a little bit, but this 10 degrees is going to raise up a lot more. So this is how these calculations work. I'm going to use the same relationship for our next scenario, which is scenario 3. We've got two objects with different materials and different masses. And the thing is, we need the heat capacity of both. So here's the heat capacity of copper, and we have water at 20 degrees. The heat Cp of water is equal to 4.184 joules per gram degree Celsius. Again, we're looking at heat flow. Heat flow going away from copper into water. And this is, I'm going to use this same relationship again. Remember, this is heat from copper is equal to the opposite of heat gained by water. And we can have this on either side, doesn't matter. So we're going to pick the left side as copper, the right hand as water. So we're going to move this and go M1 TF minus TI of 1. Now the temperature final has to be the same between both. And this is the heat capacity of copper, equal to minus M2, that's the mass of water, temperature final, T final of 2, and then heat capacity of water. Now heat capacity is going to be different from each one, so we can't mess with that yet. So what we're going to end up doing is going mass of 1, Cp of 1 of our copper, times temperature final, minus mass of 1, heat capacity of copper, of Cu, times initial temperature of copper. That's equal to the negative mass to final and Cp of water, times final temperature of water. plus M2 CP of water. Let me put H2O down here because that's what we're dealing with. Initial temperature of H2O. We said mass M1 is equal to 10. M2 is 100 grams, I believe. Let's go back up here. Yep, 10, 100, 80, and 20. So Ti copper is equal to 80. Its initial temperature of H2O is equal to 20. So we'll put all that in. Now, heat capacity CP of copper, again, it's going to be 0.385. CP of water, I know by heart, 4.184. So this is going to be a bit messy. 10 times 0.385 times our final temperature, which we don't know. That's what we're looking for. Minus 10, 0.385. And now we're going to multiply this by 80. That's equal to minus 100 times 4.184 times the final temperature, which you don't know, plus 100, 4.184 times 20. All right, so what I'm going to do is take this, add it to both sides, so move it over to the left. And ladies and gentlemen, since we have a plus and minus, I get to add them both. For a lot of you guys, this is the first time I get to do this. Plus 100 times 4.184 TF, and that's my cat, plus 100 times 4.184 times 20, plus 10 times 0.385 times 80. We're looking for TF. So I had to move the cat. So the right-hand side, let's go ahead and get this number together, 100. Times 4.184 times 20. Then add to that 10 times 3.385 times 80. And we're going to get 8,676. And on the left, this is going to be 3.85 TF plus 408.4 TF. Add those two together, and we're going to get 422 TF equals 8676. Now we're going to divide TF 422 from both sides. So the final temperature is equal to and I'm going to say 422.25, excuse me. .55 degrees Celsius. Water cools down the metal a lot, but the initial temperature, rise in temperature, it's not that much. And this is common. This is why water is such a good cooling and heating system. This is why we cook food in water, because the amount of energy it contains, which can heat the food, is tremendous. So this is your final answer. Granted, this is long. Have a good day, folks, and we'll talk to you later.